Hello, I'm Mrs. Stevenson. Conductivity of doped silicon. Silicon is doped with arsenic so that 1 in every million silicon atoms is replaced by an arsenic atom. Each arsenic atom donates 1 electron to the conduction band. What is the density of free electrons? B. By what ratio is the density greater than that of intrinsic silicon with 1.45 times 10 to the 10th free electrons per centimeter cubed? And C. Is conduction mainly by the electrons of the silicon or the arsenic? When silicon is doped with the arsenic atoms, there is 1 extra electron to move from atom to atom when thermal energy is added. This is what's called an N-type semiconductor. In order to solve this problem, we first have to write down our knowns. And we know that there is 1 arsenic atom for every 10 to the 6th silicon atoms. We also know that there is 1 free electron from every arsenic atom. And we also can determine that there are 4.99 times 10 to the 22nd silicon atoms per centimeter cubed. This number comes from the density of silicon. And we're also given that there is 1.45 times 10 to the 10 free electrons per every centimeter cubed in intrinsic silicon. The unknowns for this problem are that we are looking for the free electrons per centimeter cubed donated by the arsenic. We're looking for also the ratio of arsenic donated free electrons to intrinsic free electrons. Okay, in order to solve the first part of this problem, we are looking for the free electrons per centimeter cubed from arsenic. We are going to manipulate some of our knowns and do some unit conversions in order to figure out the free electrons per centimeter cubed. We're going to do this by taking the free electrons per arsenic atom and we're going to multiply that by the number of arsenic atoms per silicon atoms. We're going to multiply that by the silicon atoms per centimeter cubed. And we're going to cancel out units. So we see on the bottom here, we have arsenic atoms, and on the top we have arsenic atoms. So those cancel out. We have silicon atoms on the bottom and silicon atoms on the top, so we're left with free electrons per centimeter cubed, which is what we're looking for from arsenic. So we're going to plug in our values that were given to us in our knowns. So we have 1 free electron per 1 arsenic atom. We also know that there is 1 arsenic atom per every 1 times 10 to the 6th silicon atoms and we also know that we have 4.99 times 10 to the 22nd silicon atoms per centimeter cubed. And our units are going to cancel out just as they did before, so we find that our final answer is that we get 4.99 times 10 to the 16th free electrons per centimeter cubed from arsenic. Now, if we want to look at the ratio, we need to compare the amount of free electrons per centimeter cubed in doped silicon, which is what we have, compared to the free electrons per centimeter cubed in intrinsic silicon. We just determined the number of free electrons per centimeter cubed in doped silicon, and we were given the value for intrinsic silicon. So we're going to plug in both of our known values. So we're going to have 4.99 times 10 to the 16th free electrons per centimeter cubed in doped silicon from part A. We're going to divide that by our known value of 1.45 times 10 to the 10th free electrons per centimeter cubed in intrinsic silicon. We get an answer of 3.44 times 10 to the 6th arsenic donated electrons per intrinsic silicon electrons. And because there are over 3 million, or 3.44 times 10 to the 6th, arsenic-donated electrons per every intrinsic electrons, conduction is mainly by the arsenic-donated electrons.